So, welcome again to the second part. The purpose of the first 5 minutes is to deal with polar plots. How many of you have already used the polar plots in the past? None, but you have heard about them or not? Okay. So, well, you represent not only angular or periodic data, so there is this radius, this distance from the center, and then the angle. Okay. Let us open this file. First of all, let us see what we want to achieve. So, we start from the data set with the sales of ski and water ski that we have already seen previously. So you see that these are represented by arrows which depart from the origin. So you can see here, for example, there are the months. Of course, this is 360 degrees, so these are 12 months. Therefore, what will be the degree from year to year? What will be the degree from year to year? 30, of course. Yes, 12, 30. So 30 times 12 is 360, right? Yes. Okay. So, you create this sequence, a sequence of 0 degrees that has a step 30, and then it goes up to 330, because it is a sequence of 12 terms, right? So these are degree to radians, and then you have the sequence in radians, okay? So is a sequence of 0, pi divided by 6, and so on and so forth. So that's the reason why here I do this sequence theta. This theta sequence in radians, right? Can you recognize that this is pi? So this is 180 degrees, right? So theta, so therefore rad 2 degree theta, and this is the sequence, right? Same thing, or in degrees or in radians, whatever you like. Okay, then here in the compass plot you have theta, how the angle is divided, and then you have your matrix. And then there is compass plot. Okay, you see that there are the degrees there, eh? Okay, the purpose is once that you put the variable names, you put the tick labels, then you see that the arrows here prevail in October, November, December, and January. On the other end, the arrows prevail in the months of May and June. So these are the sales of these two things that are much more relevant during summer or during winter. And then these are now the legend. When do you sell the ski? Mainly October, November, December. When do you sell the water ski? Mainly in June, July, and May. So you prepare for the summer. So therefore, this is the idea of this compass plot. Now I tell you what is our purpose And our purpose is to discuss the polar histogram. We all know what is the histogram. A polar histogram is a histogram in polar coordinates. So around this circle. So we have created a function which is called polar histogram fs. So that lets you create immediately this plot. And let us see it. File is polar histogram main. So in the first part of the file, there is the manual construction of the plot, just to tell you what you want to achieve. So you see, north and center and south, and these are the classes. The classes of added value. First of all, let us see the output. Let us comment the output. Now, can you see the center and the south, and then they are characterized by low value of added value? On the other hand, the regions or the provinces of the north have a much higher value. Can you see it? This is clearly shown in this plot. And this is classes where there is the intersection of both. Okay? So you can, let us see, you can see these things either in this way, either in this way. Let us see both of them together. Which one do you prefer? The circle. Yeah. So you see these three classes correspond to the first three. And can you see here that there are boats here in the fourth class? And look at here, because it's 7, 7, 7, 7, so 14. Is they're equal, right? But this is surely much better, eh? And what you want now to do it, you want to do something which is for all the variables. You see, because it's a multivariate thing, so you want to see what is the difference between center and north for added value, it is clear. Deposit, it is clear. Pension, it is clear. Export is also clear. Bankrupts, more or less is the same. As we said before, high level of bankruptcy are for both coexist for low and high income. So corruption does not depend on the level of income. Right. Because one person can be very rich and corrupted or very poor and corrupted, yes. Corruption is something which is spread. So this is the thing which comes out immediately. So now, how do you do it? So, well, if you have a table, if you call polar histogram fs with the table, we try to simplify things. So polar is our function. Polar histogram fs does the job for you. Because in the compass plot, you have to divide the angle, you have to create the sequence, and then to apply the label. Well, these engineers are very, very good, but you want to have a function which does everything for you. Call polar histogram fs your table, and then you must be able to do the thing. Yes. So you see, that's the thing you want to do. But this is the global thing. On the other hand, what you want to create is a variable which is called zone. Zone, because the first 46 provinces refer to the provinces of the north. The others refer to the provinces which belong to the center and south. You understand this thing, REPLM? It means a repeat element. For example, repeat element n 3 times, and this is what you get. Repeat element 2 times 3, and then repeats in a matrix 2 times 3. And so you say this n is repeated 46 times, CS is repeated 57 times, given that this is a row vector, and then it becomes a column vector. You see? And then here there is the group invariant. So polar histogram FS as the group vars is the group invariable, and data vars the variables that you want to use. That's it. Then polar histogram FS has all options that polar histogram has. For example, if you go to the histogram chart on polar coordinates, then you go to the name values, and then you can see all these options. Type of normalization, for example, display style bar default, and there is stairs. You see display style. And let us see what display style stair is. So the same thing, but we have display style and line width. Of course, line width is a bigger line width. Okay. Data vars dv, I mean the variables that you want to use. Group vars is z3, this group invariable, number of bins for 10 classes, and let us see what display style stairs is. Right, so if you don't want an overlap among the colors, then you put a display style stairs, so there is not an overlap in the colors. You prefer this version or the other? The other, eh? Ah, well, you know, because on the other end, for example, I must say that I prefer this one, eh? Well, but, yeah. You know, what I would like to do in the future is to click on these legends and then to hide the associated thing. But this is not so easy. I need 4 or 5 hours staying tranquil and to program it, which 4 or 5 hours staying tranquil in front of the computer. Now, in my case, I guess you can imagine. Or I throw away my mobile, the computer must not be logged into internet, otherwise it is impossible. However, by the end of the course, however, I wanted to do it, because it will be a nice addition in the Word community, to click on it and then to hide or show the associated line. And then the other benefit is that here you can see the classes. You can see the starting point and the end point of the classes. If you have the histograms, you don't know what the classes are. So this is an additional benefit. But this is, this is our function, polar histogram FS, which is very easy. You have your table and then you plot it, and that's it. Because the compass plot, well, you have to divide, you know, it is, then you have to transform your data inside 360. Because what do you do? Just to give you an idea. You transform your data, you normalize your data into 0 and 1. Then you multiply by 360, so your data goes from 0 to 360. That's the trick. Because then all these are mapped into 360, and then you put the original labels. That's the trick which has been used. Okay, now, parallel coordinates. Have you already seen this? Some of you have already seen it. In general, do you know this way of plotting the data? Right. Have you ever seen it? Never? Yes. But they are very effective, So you have P equidistant parallel axis, then for each unit you compute eventually the standardized variables, and then you connect the profile. You have a polyline for each unit. A polyline for each unit, which shows the profile of each unit. Okay. These are the two functions which enable to do it in MATLAB, parallel plot and parallel chords. So let us see parallel plot. You see the two, okay, parallel plots. Parallel plots, and let us see an example here. Let me do close all, clear all, so that everything is deleted from memory. Okay, load patience on the other end is a MATLAB dataset, patience. If you do load patience, it loads a series of variables referred to a series of patients. Then you do table, diastolic, smoker, and systolic. So you create this table which has these three variables. Therefore, this blood pressure, you have diastolic and systolic, and then you record the fact that the person is smoker or not. The question is, those who are smokers tend to have lower or higher diastolic and systolic pressure? Higher. Yeah, it is true. They tend to have higher pressure. Now, we check if this is true with this sample. So this is called TBL, parallel plot, TBL, our table, okay? That's it, yes, that's it. Yes, you see, 93 through 124, here is 93, where is this? 91, then 93, 92, 93, 1 and 24, and this is for the first row. So therefore, each one has a polyline with the three values. Now, what do you see in general? In general, you see that those who are smoker tend to have values of the two pressures that are slightly higher. And this is very effective. In this case, smoker, it makes sense to put smoker in the center, because if you put it on the right, this is what you get. You see, I've moved the smoker from the second to the third position. And now, here it is not so clear here what is going on. Isn't it? So it's better to put back a smoker inside. But this is MATLAB, and what is impossible to do in other languages, in MATLAB is just drag and drop. Of course, it has a license, you pay, clearly, nothing is for free, but this is a sort of Ferrari, if you know what a Ferrari is. You all know what a Ferrari is. So we are driving a Ferrari. At least if you don't have a Ferrari in a car, at least you have a Ferrari in computing. At least a small part. You cannot have the overall thing, just start having a small piece of it. And look at it. Then it automatically the polyline is shown. Okay, can you see? Okay, now I want to understand whether you have understood the intricacies of the parallel coordinates plot. Now, here we have to generate a data set which has 9 variables. The first 5 variables have a positive correlation. Have you seen the previous example where we put together the variables which were strongly correlated? Now we have to generate the data in such a way that the first 5 variables have a stronger positive mutual correlation. The remaining 4 have strong positive mutual correlation among each other, but are strongly negatively correlated with the first 5. So it is clear. First 5, positive correlation. From variable 6 to 9, positive correlation among them, but variables from 6 to 9 must have an inverse correlation with the first 5. We do this exercise from scratch or not? From scratch. I hope not, to be sincere. Okay. Okay. Right. Okay, you want to have M file or MLX? MLX? Okay. Create first 5 variables positively correlated. Okay, then in fact this is wrong. In fact, what the copilot proposes is wrong, because these are random data and therefore fixed variable. Let us accept it. Now, if I do this thing, SPM plot, y is equal to y1, y2, y3, y4, y5, really beginner's code, the one generated by the copilot, clearly. SPM plot y. What do we get here? And then, okay. You see what he has done. He has done. First, he has created X, and then he has done the y1 is X plus a random noise. The second variable is X plus another random noise. So the difference is really very, very small. And this is a possibility, you see. This is a trick. So here it starts from the same random numbers. And then to each column it adds a little bit. Let us parameterize it a bit more. Maybe instead of let us write sigma here. Sigma, and sigma.
In place of x?
In place of 0.1, right, yes.
In place of x, x plus, for example, y2 is equals to y1 plus, if you make it
yes.
chain like a chain.
Yeah. In fact, I wanted to reach that stage. Let us go. So, for example, here if you put 100, what do you get? You can see that here random noise times 100 prevails on the x here because you multiply by 100. So the noise here plays a very important part. Therefore, when you do the SPM plot, this is what you see. Right. But now you know what, given that now we want to do insert a slider. Okay, here insert a slider, but did I... okay, live editor. control slider. Control slider, okay. Slider, and here configure control, so the minimum is 1 and the maximum is 100 and the step is 1. Default value is I don't know, 80. Okay, let me save it, and then example PP. Okay. So, look at the program that I've created. I've created this slider. So, if this slider sigma is 80, sigma is much smaller, then a moment, then the variables become more and more correlated. Sigma is equal to 9. Let us see with sigma is equal to 3. Then let us see the code. Let us see the code. Therefore, this is sigma, and here I want that configure control. I want that the minimum value of sigma is 0.01, and then the maximum is I don't know, 10. And the step is 0.1, and the default value is 5. So if sigma now is very small, this is what you get, you see. Now let me hide it. You see that if sigma increases, then the degree of correlation among the variables decreases. Can you see it? If sigma becomes larger, then the points don't have any correlation. You see that this is what plays the game. Now look at very small value of sigma. Small and smaller and smaller, and then they tend to be more and more correlated. Yes, you see now. You see.
The bigger the sigma, the less correlated.
Exactly. Because you see the code, you see is x plus something which is a random noise times sigma. If sigma is greater, this means that this part prevails on x. Okay, then, okay, this is a way of generating it that is a little bit from beginners, so we remove it, okay? Yeah. So we say then x is equal to zeros, and then here instead of writing here we write n, and so n is equal to 100. Let us see the exercise. Create a 100 times 9 matrix x as follows. So n is equal to 100 and p is equal to 9, right? Okay. X is initialized with zeros and p, right? So the first column of y, first column of x, yes, random numbers. There was a question. So you see the first column of x, just random data in the. I could not hear.
X zeros in piece. What is zeros?
So you have 109. N is equal to
functions. Zero function.
Creates zero n. So this is how you initialize, generally you initialize things. So for example, Tell me. Yeah? Because this is a function of FSTA, so we have to download FSTA. FSTA is our full we have created. So, okay, you all will be able to install FSTA, so you are going to show him how to install FSTA. Will you do it? Okay. This is the first page of the book, how to install FSTA. Okay, however. One moment. So, zeros 2, 3 creates a matrix of 0 of 2 rows and 3 columns. And so, generally, you don't know how to initialize a double, you initialize it with zeros. So, therefore, this code X creates a matrix of dimension 10 times 9, which is full of zeros. Then you have to fill this matrix, goes without saying. And how do you fill it? You fill it, the first column, you fill it with random numbers from the normal. And this is the preview of the code. So the first column. Now you have to fill columns 2, 3, and 4, 5 in such a way that variables 2, 3, 4, 5 have a strong positive correlation with the first. So 4j from 2 to 5, 4j from 2 to 5, xj is equal, for example, to x1, for example, times 2 plus 10 or whatever, plus some random noise n1. Exactly, run them in order to add a noise from the norm. Otherwise, they are perfectly. They have a perfect correlation. So, and then here we put sigma. And then here we write sigma is equal to, let's start with sigma is equal to 1, and then end. Okay? Okay, this. When Rn n1, yeah, because n is the number of rows and 1 is the number of columns, so this is a vector.
Yeah, I'm talking about sigma, the variable.
Yeah, sigma is a scalar.
Now, when you initialize sigma, and you sigma equals 1, 2 points, and then you left it, does that mean the amount of sigma is infinite, like 1, 2, 3 till the end, or that's
No.
Yeah, because you didn't include the
Right, this is a semicolon. Yeah, right, this is a semicolon, yes. So this is a semicolon, right. So this is a structure to terminate. Yeah? Y has remained from before. So let us take it easy. Y has remained from before. Now don't be too unleashed. I mean, Y has remained because there was this bloody code from the copilot and so remained. One moment, there was him, want to do that. I have to answer him. I didn't have physically the time, they are really unleashed. Yes.
I'm not the one unleashed today.
Yes, give me the time to write with the code. Okay. Yes, it is true that Y had to be deleted. Absolutely correct. However, indeed, this is the class that I want, and thank you very much. And I'm very, very happy. I don't want to have a boring thing where people listen to the teacher, do not understand anything. I really want you to be this way. So now when we do it with the run and then we put the breakpoint, so X is just the first column. And then step, so J, for the first time, J is equal to 2. So we fill column 2, you see. We fill column 2 step, and this is the the second column, right? Then step, now J becomes equal to 3, and now we fill the third column. You see, now it has filled the 3 columns, and then the fourth, and then the fifth, right? So, now let us give it a try. SPM plot, X, and then we run it. Okay, let us put here the semicolon. Right. Okay. Here we have generated just the first 5 columns, First 5. Or if you want here, you should have done something like this, 1 to 5, to plot just the first 5 columns, because all the others are equal to 0, and so there is nothing, The other is exactly equal to 0, okay. And you see that the correlation is positive. If sigma is 0.1, then the correlation becomes even stronger. You see, becomes even stronger. Okay, now equal to 1. Now, let us read the exercise. The remaining 4 have strong positive mutual correlation, but strong negative correlation with the first 5. So, for J is equal to from 6 to 9, what you do, for example, minus. Right? So they have a negative correlation. You put a minus. You put a minus there. Right? And now let us put here X. Okay? Okay, now you can see the trick, Yeah, and now let us see this plot. Let us open this window in a new figure. Right. Now you can see the first 5 that have a positive correlation. They have a negative correlation with the remaining 4. But these remaining 4 are all positive correlated among them. Okay, you see that these 4, the 4 here, they all show a positive correlation among each other, but a negative correlation with the first 5. You see? How is statistics? If you learn statistics, then you understand with the variables that are correlated, not correlated. Now, let us do the same thing. Let us do it with sigma is equal to 0.1. Run. Okay, maybe I have even exaggerated here. Okay, let us open. So you see, they are almost the first 5 strong linear correlation, and the last four are strongly linear related, but negatively linear related with the first five. Okay. Now.
Sigma value decided again strong correlation and weak correlation. Sigma value is less. We can decide
Exactly.
a strong correlation.
Exactly. Sigma, which plays the game, is this number. Because now here you are doing x1 times 2, but if these numbers become too big, they prevail on the systematic part.
Who decides the amount of sigma? The value.
God. Yes, God decides the amount of sigma, because you observe the sample, and then you have to estimate this sigma. That's our job. Right, because you observe this data, and from this data you compute the linear correlation coefficient, you compute the covariance matrix, you do all this plot and try to think, okay, God has generated that value of sigma, that value of the correlation. But now we work as if we were God, because we know the data generating process. But in practice, you don't know it. That's the thing. Who decides it? You don't know. You have to estimate it. But if you see a sample with these characteristics, then given that sample values are closer to the population values. And asymptotically, sample values, if you increase n, sample values and summary statistics tend to be closer and closer to the true values. That's the properties of the estimators.
In the last four columns, instead of making negative x, what we if we shift to parallel to the city, in place of making negative x,
Yeah.
totally the side, what we make if we make the times like times very small.
Yeah, right. Which is an alternative thing of sigma.
Is there any difference, right?
It is. But the idea is that you have two parts. Which one prevails? Right. This is another possibility to put sigma here instead of put, and then I put times 2. So.
Can we just play around have dynamic sigma and try multiple
Yes. So for example, this is, let us say, sigma 2. So the last four are not
They are strong correlated.
well, they are not correlated because sigma 2 rand, they are not correlated.
Not sigma, not sigma 2. It's
Sigma
very
2.
small. So basically,
Right. Yes. Okay. Now let us. You see, define the last four that have no correlation with the others. But you have to see this plot in order to understand the statistics. Otherwise, you don't understand anything. So, therefore, if here you have sigma 2 is equal to sigma. Okay, let us.
like literally we've done the same.
Yeah. Okay, so when we do the parallel plot, we do parallel plot X. What do you expect to see when we do the parallel plot? In this case, what do we expect? And now I show you, evaluating the command window so that we evaluate it in the command window. One moment, close all. Look what you observe. You see the first 5 variables that have a positive correlation. So the largest remains the largest, the smallest remains the smallest. But the fifth and the sixth have a strong negative correlation. So the largest tend to become the smallest and vice versa. You see this crossing. Look all this. Now this variable 6, 7, 8, 9, among them they are positively related. Now tell me, if I put variable 8, I put it among these two, what happens?
It's not correlated.
No, it is strongly correlated. Why? How? Because all of these are all 7, 8, 6, 7, 8, 9 are all
Correlated.
strongly among them.
Yeah.
Therefore, if you place it here, all these have a negative correlation with the first 5.
Yeah.
Therefore, if you put 8 inside here, you have this. Because the positive, the largest, then become the smallest and the largest again. You see the point? And now look at this, in fact. Can you follow it? You see this thing. 2 and 8 are negatively correlated. But also 8 and 3 are negatively correlated. Because 1 and 3 are positively correlated, you see? And this is what you observe, 2, 8, and 3. And now, if I put here variable 9 close to variable 8, what do you observe?
They are positive.
Yes, and so you see 8 and 9, you see no crossing, because they are positively correlated. But when you move from 9 to 3, there is a strong negative correlation. And so you see the intersection. This is how a person has to understand the statistics. Otherwise, there is no way. Right. So therefore, 3 and 4, strong positive correlation. 4 and 5, strong positive correlation. 5 and 6, negative correlation. 6 and 7, positive correlation. 5 and 7, negative correlation, because there was this crossing. Right. And so here, of course, the plots change very much here according to where you put the variables. You see here, it's the same plot as before, but every time that you put 7 with 4, or 7 with 3, or 3 with 9, and there is a crossing. Okay, so therefore that was the purpose of this exercise. Yeah.
How do we find in a large set of data where to put the middle variable, the one that changes?
Right. You do it with the technique that we are about to see in the final week. That is the technique of principal components, where you try to group together variables that are similar, that have the same sign. And this is what we have just done implicitly in the scatter plot matrix that we have seen before. In fact, this is a good question, because you have so many variables. How do you decide? So this group goes together, then there is another group. Yes, little by little. Little by little. Spanish would say partido por partido. You say partido por partido? Partido por partido. Oh, no, in Spain they say partido, no? I don't know. Anyway. So, So tell me if it is clear what is written here. They also reveal a homogeneous group of units. They point out multivariate outliers because there are lines which are different from the others. These are the multivariate outliers. For example, there is plot parallel coordinates. Then we have with the dataset Fisher iris. Then I apply parallel chords. Let us see. You see the three groups now, how they are shown with the three colors, and you see that there are two groups which overlap, and one which is very distinct from the other two. Well, instead of plotting many lines, that it becomes too cumbersome, you can plot the quantile of these lines. Right, so you just plot 3 lines for each group. And well, what else? Now, if you create an outlier, MEAS, let me close clear all. Let us create an outlier. For example, MEAS is 5314. Okay, now we say MEAS first row, I don't know, is equal to -2. So the first row, well, it is impossible that the length of this flower is -2. Then they have a negative, yeah. However, we see what happens. Yes, where is it? Where is it? Here it seems that we cannot see it. MEAS. Probably this. No. Yeah, I did. MEAS 1 is equal to -2. MEAS. So here I load the Fisher iris, and then you see that it has become -2. So instead of -2, now we put -20. -20 here, right? Okay, well, too much. -2. So let us put something like, for example, 1, 10, 1, and 8. Okay, this is the line that I've created. That immediately shows these multivariate outliers. That the lines which have a profile which is really different, yes, they will. The quantile on the other end will not be unaffected because it's just for each group you take the 25% and 75% of the quantiles. That's the idea. So yeah. Then, iconic representation. Have you ever seen this iconic representation? So each statistical unit is represented with a figure, for example, with a star or with a face. Sometimes you see each unit is represented with a face. Well, these plots were very popular in the past. Now, much less, if I have to say so. For example, let us take once again the dataset of Italian cities and the dataset of Italian cities Italy. So it has variables, unemployment, bankruptcy, and bills overdue, have a negative sign from all the others, right? Unemployment, the greater the worse is, bankruptcy, the greater the worse is, bills overdue, the same thing. Therefore, here we say that these, the first three variables plus the fifth, which are positively correlated with the quality of life, first three variables and the fifth, now I change the sign of these variables. First three plus fifth, I change the sign. You see this code. I change the sign to this variable so that they all the variables agree that the larger, the worse is. And now you represent each province with a star. And how bigger is the star? Yes, the worse is the province. So, for example, well, you can see, for example, a figure, an icon. Right. So you have 7 lines departing from the origin because we have 7 variables. If you have 12 variables, then you have 12 lines. And then you connect all these lines with a line. So, for example, you see Naples, that is very, very strong in all, because he is, is very, very bad in all possible ways. On the other end, the provinces from the north, you can see that they are much smaller. Moreover, to the icons, similar icons denote similar units. You see? So therefore you can have a first idea about so-called clustering, classification of the units into different groups. And then if you have then the outlying observation, they stand out as different stars, let's say.
Are we going to study clustering and classification?
In the next course. In the next course. Partita por partita. Yes. Then, okay. No. Agustin, sorry, now I'm teaching. I have to answer later. Okay. Yeah, but not now. Now I'm teaching. I cannot now. I'm teaching. I cannot now. Okay, bye. Bye. Yeah. I will finish at 12:15. Okay, bye. Yeah. So how do we create this plot? Glyph plot, right? Then if you have the option glyph face, and then what do you get? Now we change the sign of 4, 6, and 7. So therefore, the bigger, the better. And now we see it in terms of faces. Well, we change sign. Yeah, you are right. No, here, the bigger the better in this case, because we changed sign to. Right. We change the sign to unemployment. Yeah, but we changed the sign. So unemployment, the bigger the worst. Yeah. But we change sign, so the bigger is the better, if we change sign. So unemployment, the bigger is the worst. But you change sign, so the bigger is the better. So, and this is the plot that you get. Now with faces. Can you see the face? Now so look at the face of Rome, which is very, very different from all the others.
Who wants to see that?
Yes. And so these are small faces, and then Parma is well, quite nice face. Then you can be unleashed here because you can associate each variable to the length of the nose, to the length of the eyes, or whatever.
Is that still used?
Yes.
Why?
Well, for example, when I did a consultancy in an hospital, there was they wanted to show the patient, and then they were very, very happy. So the variable satisfaction was linked to the smile. So the greater the smile, the greater was the degree of satisfaction of the patient. Or for example, and then you have to associate a particular characteristic. Sometimes a plot is much better than 1,000 words.
Yeah, blood is always better, but the faces are creepy.
Okay. In fact, I'm not staying 4 hours showing the Chernow face. I'm showing this thing for just 2 minutes, so that you know that these things exist. You never know. And that's it. Okay. And now we are ready. Okay, then there are other plots like these donut charts or the break-even point, graphical illustration with the break-even, with these slider bars. Well, but you will be able to see. Now, measures of association. So, when we talk about correlation, we have in mind quantitative variables. When we talk about rank correlation, we have in mind variables which are at least qualitative but ordered qualitative variables. When we talk about association, then we have in mind categorical data, nominal or ordinal. So now we deal with association. So association for contingency table. And now we start with the 2 times 2 table. So is dichotomous binary variable, but actually these tables are very general because every variable, for example, income, can be cut into 2 parts, those smaller than a certain threshold, those greater than a certain threshold. So dichotomous is not something which is, not possible to find. It's very common. So here there is a main tabella, or anyway, table. So for example, here, look at the notation. Are you familiar with the notation N1 dot? So the number of observations, total number of observations which are in the first row. Are you familiar with N dot 2? The number of observations which are in the second column. N11, the number of persons who purchased both products A and B. Yes, so it is a product A, product B, and then you count the occurrences. You count the numbers. And N is the total sample size. Okay, are you familiar with this notation? I hope so, eh? So, for example, if you have a 2 times 2 table, and then if these numbers are fixed, are given, the marginals are given, inside you have just so-called 1 degree of freedom, because you can put just one number as you like, but all the other 3 are given that the marginal are fixed. For example, if you have these numbers that are fixed, if here you write, I don't know, you write 15, what is the number that is here? 25. What is the number which is here? 15. And what is the number which is here? 35. Right? So, given one, all the others follow. So therefore, this is why we say that there is 1 degree of freedom. The possibility of putting just a single number as you like. Of course, but the first number 15 cannot be greater than what? No, cannot be greater than 30. But the total, there are 4 totals. The total of what? The total is a bit vague at the total. The total of the let us say, the mean between the total of the first column and the first row. Because the total is a bit vague. There are 6 totals. Okay. Okay, so you see this statement. Now, let us do a summary. Have you already seen the Bayes theorem or not?
What?
Bayes theorem.
Bias.
Bayes. Oh, Bayes. Right. Yeah. Bayes. Right. Each of you has done the Bayes theorem. Right. So, now let us see. You understand the probability of A given B. If B took place, your possible space, your possible space is the one of B. So the probability of A given B is just, let me delete. So the probability of A given B, these are the possible cases. On the other end, these are the given B, these are your possible cases, but these are not the favorable cases. The favorable cases are inside this part. But given B, otherwise the probability of B is this area divided by the overall space. That's clear, eh? Right. So, if the conditional probability is equal to the marginal probability, if the conditional probability is equal to the marginal probability, or if the intersection of the probability is equal to the product, that the events are independent. Right. So this is the basic rule. The probability of the intersection is the product of the probability if the two events are independent. Right. So therefore, if the two events are independent, means that knowing B does not affect A. So you say that the joint is equal to the product of the marginals. Now, what are these concepts in terms of our contingency table? Now, what is the probability of observing x1 given that y is equal to y1? So, if I is equal to y1, so you do not consider this thing because y is equal to y1, right? Given that y is equal to y1. And what is this probability here? What is? Given that y1 is given that, yeah? It is this one divided by this, right? Okay, can you see it here? This one is this, right? See if, okay, given that y1 took place. Okay, now you now we have the probability here. Y2 has shown up. y2. y2, therefore, you know that y2. What is the probability of observing x1 given that y2 has shown up? n12 divided by n.2, right. On the other hand, what is the marginal probability of observing x1 without knowing the value of y? It is n1 dot divided by n. Can you see it? The final one. Let me show you with this one. So this one here, the final one, if y is not known, if y, the value of y is not known, you just have these three numbers, okay? What is the probability of x is equal to 1? n1 dot divided by n. Well, if all these three equalities are true, you see that now, let me, you see if all these three equalities are true, then, if all these three are true, then you have then a formula in order to compute the theoretical probability. So you know what is the theoretical frequency under independence. Right? So let me see. And the interpretation is that the proportion of statistical units present in category x1 of x does not depend on y. So, for example, this is an example where you have the memory of an advertisement and the product purchase. So, 87 are the number of people who do remember the advertisement, but who bought the product. Those 406 are the person who do not remember the advertisement and did not buy the product. Now we have to create the table of expected frequencies in case of independence. What do we expect? So the idea is, let us compare these numbers with the numbers that you will get if the two variables had been independent, because this is a sample, and it's clear that sample values differ from population values. This goes without saying. So, how do you compute this expected frequency for yes? Let us go back. You see, Nij star is equal to the margin of the rows times the margin of the columns divided by n. Right? This is the formula. Therefore, here what you do, the theoretical frequency here is 199 margin of the columns times margin of the row divided by n, right? 49.1 is the expected frequency in case of independence. So you have observed 87 and the expected frequency is 49.1. Note that given this number, this 79.9 is given that 129 remains fixed. So you can just compute one and all the others are immediately generated. Okay, with the computer, you compute all of them, and however, so we say that there is a positive association, in Italy, associazione positiva, positive association, if the real frequency is greater than the theoretical frequency, which is our case, because the real frequency is greater than the expected. Now you have to check whether this 87 is significantly different from the value that you obtain under the null hypothesis of independence. And that's statistics, because you want to see whether the advertising campaign is fruitful or not. But you have a benchmark, and the benchmark is the theoretical frequency under independence. So you have a negative association, of course, the advertisement agency is immediately sacked if you have a negative association, means that if you remember the advertisement, then you don't buy the product. You know, this happened in Italy in 1994 when we lost the championship match of the World Cup because our Roberto Baggio didn't score a penalty, so we had an advertisement, then they pretended that Roberto Baggio had scored the penalty. So it is clear that all Italians were furious because we were all very angry, and so this advertisement campaign was a disaster. A disaster. So, okay, this is, you have to choose a reference category, and the choice of the reference category is arbitrary. Okay, now, there is a statistic which checks whether the difference between observed and theoretical frequencies is significant or not. This statistic is called the chi-square statistic because it is distributed as a chi-square random variable. A chi-square random variable is the sum of 4 terms, but remember that you have just 1 degree of freedom, and in fact it is distributed as a chi-square with 1 degree of freedom. So you see it is the sum of squares, therefore these statistics cannot be smaller than 0. The greater, the larger is the difference between effective and theoretical frequencies. So it has a chi-square distribution, but then we have seen the distribution of the chi-square anyway. So the value now, if you have the chi-square, now if you multiply all the instances of the table by 10, what happens to the chi-square statistic? If n11, n12, n21, and n22 are multiplied by 10, what happens to the statistic? The statistic remains the same. How does it change? If all the entries of the table are multiplied by 10, what do you think? The same? No, it's not the same, because here you see you multiply each element by 10, but then here there is the square, and so becomes and here you divide it by 10, therefore it is multiplied by 10, right. Therefore, if you double the sample size, your statistics is multiplied by 2. Right. So therefore, these statistics, you see here, depends on n, and tends to increase as n grows. Therefore, you want to have a relative measure which does not depend on n. Well, if it depends on n, then you divide by n, so it does not depend anymore on n. And then this is the formula. This is the formula where there is a plus minus, because the indicates that square root is assigned the sign of this difference. So this phi coefficient is something which is in the interval -1 and +1. And indeed can be interpreted as a correlation coefficient. When do you have the value of 1? You have the value of 1 in these particular cases, which means that all those, for example, who have bought the product are all those who have remembered about the advertisement. And all those who did not buy the product are all those who have not seen the advertisement. This is the ideal scenario. If you see the advertisement, then you buy the product. If you don't see it, you don't buy. Well, you become a millionaire if you have a contingency table like that. In this case, your index phi is equal to 1. The opposite. Here it says that you have seen the advertisement. There is no way you are gonna buy the product. Those who randomly bought the product are only those who did not see the advertisement. So in fact, this phi is then you see then that these are the mathematical conditions for which you have these extreme cases. The extreme cases are called absolute association. See, all the statistical units that have X also have Y and vice versa. Now, here you can see all these calculations, and this value is 0.283, and these values can be interpreted, this phi can be interpreted as a correlation coefficient, because inside the contingency table, you can compute the mean, you can compute the variances, you can do everything. Now, if you compute the correlation coefficient, you end up with the value of phi. It's incredible, eh? So, therefore, this phi is a correlation coefficient for a 2 by 2 contingency table. And if your phi, for example, is equal to 0.28, means that the association is about 28% of the maximum absolute association. So there is a positive correlation between the advertisement and the purchase of the product, but this is 28% of the maximum. So the association is significant, is 28% of the maximum. And this in exercise 9.7, we ask you to explore all these things. If you want, maybe we can also see it jointly tomorrow, but this is the correlation coefficient. Now, there is another measure which is called, probably you have heard, the so-called cross-product ratio. Have you seen, if you watch the football matches, there are the bets, the odds. Did you hear about the odds? And so this is a ratio among the odds. So, what is the ratio between bias and non-bias? For those who know, who remember the advertisement, divided by the ratio between bias and non-bias. For those who did not watch the advertisement. So this theta index is very, very easy to compute. Is as a lower bound which is 0, as an upper bound which is infinity, and is equal to 1 if the variables are independent. So 1 is the benchmark. Therefore, you see these if the variables are independent, then you replace their formula, and then you can easily end up with the value of theta 1. So the cross product ratio, you change the column, you swap the column, the value remains the same. You swap the row, the value remains the same. You multiply the frequencies by a number, remains the same. And so it has all the properties of the world, and then it is very, very simple. And then if theta is greater than 1, there is a positive or direct association. So this is the computation of the index, which is very, very easy. Well, it is, the product, the elements on the main diagonal. So divided by the elements in this second diagonal. However, let us see the interpretation of this number, 448. The ratio between purchaser and non-purchaser is 0.462. for those who recall the advertisement. And the other ratio for those who do not recall the advertisement is just 0.10. Therefore, then, knowing the advertisement implies that you have a ratio between buyers and non-buyers which is 4 times or 8 times greater. If you remember for those who remember the advertisement, then the ratio between buyers and non-buyers is 4.48 times greater. That's the interpretation, which is very, very simple. So is something which goes from 0 to infinity. So in case of independence, you have 1. So it's 4 times 4, 8 times greater than 1. Right? And then, well, what do you do if you have an index which goes between 0 and infinity? If you want to reshape it into -1 and +1, you choose a function that maps the interval 0 infinity into -1 + 1, and this is a possible function, right? So and this is another possibility. Then so they have this Q that goes between -1 and 1. And then this is another possibility. And all these things are explored in file theta and Q. So you see the computation are very, very, very easy. So how do you pass from here to here? 0.635. This means that the association measured with Q is 635 times is 63.5% of the highest possible value. Positive. Now, what is given that the marginal are fixed? What is the maximum value that this number can achieve? Tell me. No.
53.
Oh, 53. Cannot be 72. Why?
Because
This is the maximum number. Because here cannot be 72, because the total here is 53. So this is the case of association, which is called complete. The maximum possible association, given that the marginals are fixed. So, and then if you want to compute all these indexes, then you can compute all of them. Now, if your contingency table is of size I times j, and then, okay, but we are gonna see it, yeah, we're going to see it, okay. You know, as usual, I want to tell you many things, and usually I go away that the amount of things that I have told you, the amount of things I would have liked to tell you are significantly different. Okay, anyway, thank you.
Thank you.